但是好像现在不是，反正知道什么，就是它有一些重要，也会点那个点。你那边什么？我找到那个宾客，哦，跟那个 stable 的那个 N，反正对，然后他就跟西安这里关系，然后这个岗位是比较就3号跟对，这个我现在目前是要是解这一点啊。其实什么都还没做，只是把那个给我找到一本书啊，是可以写那个还是自己介绍的，那个时候就是开始那个叫模子啊，传啊，我知道，他自己讲，他前几天直接讲，他就用他的影片，就是那个，然后那个我的第一丢，还有之前几个丢了，他帮助他，还是我要，所以我可能要把那些我可以啊是哦，是哦，可能。我在这里，应该有帮助。直接放，然后直接能够选一些不同的，对我就可以用是几回习惯。希望是这样子的，因为我其实虽然有那个口证，但是我不知道它里面那个是什么东西，或者想这方面，这个是对，这里面就是我觉得是，因为我现在是会比较注重一个故事，现在是关注个人，所以我是尽力把那个故事讲出来。我觉得对吧？是蛮好的。这个其实是啊，差不多8点半的时候，我没有自己的办公上的这个。我自己的话是有想问他讲古话很多，对我来讲其实也是顺便。
OK，下面他们呢？我没上过。Interesting。你说你刚才没有去上课？啊？ Okay, let's start. Okay. Right. So I have uploaded the tutorial sheets up to last week, and then so these tutorial sheets meant to help you with the final assignment. So the final assignment is out. So final assignment will be consists of 20% of your assignment, right? Because your assignment got 40%, and then you finish 20% already. So this is the other 20% squished into one assignment. And then so the total mark for this assignment is 100. So you can treat it as an exam. But this exam has more time. I gave you time up to the Wednesday of revision week, and you cannot extend because there's no more time for you to extend. You also need to key in mark. And then yeah, so that's it for the assignment. So if you have any question, you can discuss, but just don't copy Seng rules. Yeah, so please start as soon as possible. Start doesn't mean that you finish it, but you have to start looking at it. Okay. And one thing I need to update you. So okay, for our seminar, right? I already met with two of your group. Okay, so I'm gonna make another group today, and then the last group on Wednesday. So basically, let's see. So basically, let's see. Yeah, so I have update the course info for you. Right. So for those who have met me, right? Did you change your topic or not? If you change your topic, please let me know. Okay, I will update it because I need to come up with a seminar schedule. Okay, so please update me. If you haven't uh, I mean, if you need to update your topic, so please check with your group. And then for the other group, I will confirm it and I met you. For those who have already met me, please check if these are the topic you want to keep. Okay. And then so I think is this two telling me that they have something to do on that day, so they need to switch their thing earlier? Is it this two group? Which group? Oh, one of the group is okay, this one repeated. I remember this group need to start earlier. Right? Any other group tell me link need to start earlier? Or Justin, huh? Okay. Okay, then this is right. Okay, so these two will be finished before lunch. And these two will be after lunch. Okay. And right, so yeah. Okay, so for the content, right? So for the content, I think we will make it very close to your FYP. Okay, so first thing is you to write your abstract. So abstract is really short, not a long thing. And then this abstract is just to write what you have done in that paper. I mean, okay, in that project. If you have any thing you need to refer, right? Well, you can try and refer to my paper. So you can search me. Let me show you some paper. For example, this one is a little bit different to the method. So go to my paper, right? Okay, so you can see the abstract is really short. It just constitute of what's the main thing you did. That's all. Okay. Only intro you go and tell people or where this come from. Okay, and then what can this do? And that. Does that make sense? So abstract is just tell people, oh, I've done this paper. Is it? No need to tell people what's that because that one is for those who know the subject, then they can start their interest to read. When you read your textbook, did you read your preface intro? You got one? When I was young, I never read. I don't understand. But after I do research, I know that that one is actually pretty important. Because you think the book so thick, how you finish that book? Actually, intro is the place where you can finish that book. Okay, I mean finish that book without like understanding much, but you know that what's going on in that book. And then you know where to find what you want through people's intro. People will tell you in the intro. So my supervisor, right, when we write paper, right, he just check our intro. If our intro is good, that means our paper is good. If your intro is not good, that means you don't really know well your subject. Okay, so the intro is really important actually. Okay, it's the most important part of your paper. Okay, it tells people what's. Okay, so abstract, intro, and then set out the theory. This one really depends on your topic actually. Okay, so this part is where the technical part lies. Your definition, your theorem, your proof, everything is inside here. And then this one is actually optional. Question and possible approach. So this is the main reason why I do project actually. I want you to like do extension thinking. And so you can have your own topics. And then this topic maybe might lead to your future. Maybe your FYP can do that, or maybe your master can do that, or maybe your PhD can do that. Okay. So it's very important. So if you got it's good, if no, never mind. And then definitely put your bibliography on. Okay. Do you know how to set out your bibliography or not? Peter got issue on this. Like he very stressed on this thing here. Bibliography, do you know how to put bibliography? How? Do you like don't cite anything and then just put bibliography? It's not like that. Okay, when you put bibliography, right, this match that say that you actually refer to those stuff. So we really need to write it inside your body. Where do you refer to these things? Okay, for example, in 1955, this guy proved this. And then you should cite this paper. Right? Definition, never mind. Definition. Okay, there's one thing we can cite in general because for sometimes, like, we want to introduce a theory, but we're not going to do all of them. Right? So, for example, for the theory of curve, for the full treatment, you can see this book. But today, we're going to just help about this definition. So you need to tell people where I can read about the whole thing. Okay, if you're not going to tell people the whole thing, you need to tell people where I can see the whole thing. Correct? Make sense? Does it make sense? Okay. Okay, so this is the 5 things you need to be sure that to put in. Okay. So this Wednesday we will have Imperial College London students visiting us in the math study group. So if you can appear, then it will be good. Can talk about maths with him. I think I will invite him to our Saturday seminar. See ya. Yeah. And then I'm hoping that maybe the student council and advisors can advertise this event for those who are interested can come. Yeah. Yeah. You told me. Who did you tell? The student council. You guys don't have a poster or? Well, I'll give some info. Let's see how you're gonna advertise it after I get all the topics done. Okay. So the topics here that I have on hand is these. Okay, so if you have any change on your topic, please tell me the latest by Wednesday. Okay, otherwise I'll just use whatever you told me before. Yeah. Okay. Any other questions? Yeah. I don't know. This one is based on last time. Maybe you have changed, so let me know. Please let me know soon. And yeah, and then the order I think is pretty much like this. So we'll go with the toric variety. Toric variety actually the treatment they do is very similar to the we did in our course for our fine case projective things. Okay, and then now standard that stuff. but they go a bit advanced. They go topology stuff. Okay, because some of them learn algebraic topology before. Yeah, learn something. Usually, I know this one. I haven't fixed it. Haven't fixed it. Later, you give me the full list. Yeah, let me know the full list later. 组内顺序 you have to decide yourself. Obviously, because your topic also not here yet. Yeah, you haven't met me yet, right? This week. I only put out for those who have met me. Yeah, but if you haven't update your topic with me yet, please tell me your latest one. So I think this is pretty much the order. After toric variety, we'll do Hilbert schemes, and then after lunch we'll do elliptic curve and modular form, and then last one we do Mackay. Okay. So to motivate this Mackay, right? If you have you seen the latest lecture not yet? Sorry, not lecture not assignment. So I put the last question as a blow up. So if you confused or wonder, please come to the seminar to learn about it. So I put the assignment here. So last assignment will be consists of 100 marks. It's a 30%. Yeah, so it's almost like an exam, but I gave you more time. Okay, so last question you need to do blow up. Okay. Okay. Any other question? So to do this assignment, the tutorial is pretty important. So make sure you will go through the tutorial. Okay. So in the end, I decided not to put a divisor in here. I scared that there's not enough time to digest those stuff. So we will do up to blow up. So it's about dimension, blow up, and then a bit of rational math. Okay. Some of the things are what we have done different way, but some of the things you need to go through. So, okay. Okay, so far any question? Anything I missed or not? Anything I missed? Okay, we are actually very close to the end of the semester already. So it's very happy that to have all of you here. Actually, Eric asked me, right, why not you share the evaluation of this class? I said that, I replied that there's nothing to share in this class actually, because the student, those who decide to come here are pretty serious. What do I mean by this? Huh? Serious in study? What do I mean by this comment? You know? Maybe Lydia, do you know what I meant? You don't know. So serious meaning the student are ready to tackle their difficulty or weakness. Okay, they don't simply blame different people, right? Blame the others. So I actually want to open it up, but I don't know why the web is not good. So actually, the comment of this class is not very interesting. Huh? What's the definition of interesting? So the definition of interesting actually is based on my interest. Those are the things that I feel interested. So I mean interesting, like sometimes you very angry, make you very say very so will irritate you or make you will how to say will disturb your feeling something like that. Actually I try to open it but I cannot. So 感觉填标给你看 Actually, there's no comment there. Actually, I mean, very normal comment or too hard or something something like that, but very normal comment. Yeah. So and then the mark is okay lah. Yeah. 4.7 something, but 4.71. Hmm? Okay, I think okay. Yeah, if you like, I can show you to 满足你的好奇心 feel your curious. Who write second one? Anyone want to admit? Oh, you write one? Second point. This one you write one? Wow, thank you very much. Thank you very much. Good. It's happy if someone can appreciate your work. Huh? The what? No, no. Oh, no. No. Yeah. Good time to reflect. Okay lah. Because you see, actually not many people voting 3, but the mark is actually lower because of the percentage. This one is based on percentage. Okay, so yeah, so I wouldn't care too much, but I think still manageable. Only 2% here. 1 or 2. So actually, most of the people is like not happy about the course more than me. but actually in ANU these two things is separate one. So there's a course evaluation. There's another one is a lecture or tutor evaluation. It's a separate thing. But here they combine both. Yes, bottom is teacher, right? And then above one is course. In ANU is separate two things. So that's why in this school you could observe the course right will change pretty much follow by what the lecturer takes. I mean, quite significantly, I would say, quite significantly. But I think we have to make it more standardized. It's not like, oh, I want to make what thing you eat, what snack you eat. What's the snack you eat? Huh? Okay, never mind. I say Nike. Okay, Nike. Maybe Nike got different factory in different country, right? Okay. Yeah, sure. Okay, maybe the standard a bit different, but it can't be too much. I recognize. I mean, I acknowledge that there are difference. For example, I go Japan buy the Uniqlo, right? It's a different Uniqlo here, you know. The cloth is a bit thicker, and then it's more comfortable to wear. Actually. Then that one is, I think, is made in Vietnam, I think. And then Malaysia one, when I go and see it, oh, made in Bangladesh. Made in Bangladesh. I didn't say Bangladesh not good. I just say that the quality of the shirt. Bangladesh. Yeah. But anyway, yeah. So I guess we need to control the standard a bit. Okay. Right. Okay, and then that's it. Okay, so we remember our goal. So how is our goal? Our goal was to cover Bazoo's theorem, hopefully by this week. And then hopefully we can, I'm not sure we will prove or not. I think we won't prove Riemann-Roch theorem, but at least explain what is it. I don't think we have time to go very ample stuff, ample divisor, but I still hope I can do it. If I cannot do it, I just covered it in the notes. I mean, for my own interest, I also want to cover what is the ample line bundle stuff. And then what? And then there's one thing I want to say. I mean, forgot. Riemann-Roch, Bazoo, ample. What's the other thing? Okay, never mind. When I remember, I can tell you again. Right. Okay, let's see. Okay, so where have we been last time? Okay, let's roughly go through where we have been last time. See? Ready? Jam. Wait lang. Lisa, yeah. Over now. Yeah, so I try to fill in any gap that you would like me to fill in. This is for the sake of everyone. So I come back to teach maths, right? It's not just because of you. It's because of every one of you. Okay, so yeah, it's not just for the people in this class also. It's for actually really everyone. Okay. Hope that everyone can feel what's maths. Okay. Yeah, what maths is. What really, huh? 你不知道这个大饼跟那个大饼的差别在哪里？Okay. Yeah. So yeah. So yeah. Feel free to let me know. Okay. So anything that you don't understand, I'll try to fill it in. Yeah. Another thing for your presentation, right? So make sure that when you present, right, or after you present, actually your classmate understand what you say. Yeah. Okay. It's not like you talk gibberish on the stage like that. Okay, make sure that is your classmate understand. And first thing you need to make your group mate understand, and then only then you make your classmate understand. Okay. Yeah. Okay. So last week we finished at the definition of divisor. Okay. So what's the divisor of C? It's just some finite formal sum. Okay. Can you differentiate what's the formal sum and sum? What's the difference between formal sum and sum? Huh? Can you differentiate? Can you differentiate? What's formal sum and sum? Huh? Can you tell me what's the difference of sum and that formal sum? Hey, in this class, I actually gathered already the brilliant mind in this. I don't want to say in this school, okay, it's in the MAT at least. Okay, so try to be a little bit active. Huh? 没有，我问你 formal sum 跟 sum 啊，我问你 divisor。What is formal sum and different of formal sum and sum？好像有。
I think it's that. 那一 bracket 对，
bracket
用那个 ring of serious 的那个。
写了。Yeah. Hey, something like that, something like that. So it's like it's just a sum. For example, like this, just a sum, formal sum. Okay. Maybe if you want to evaluate the sum, okay, want to evaluate the sum. So there's a subtlety here. Okay, formal sum is just something you put together by addition. That's it. Yeah. Yeah. Okay.
I remember you saying this.
Okay, okay. So yeah. So for example, we will say that 2 is the sum of 1 and 1, right? Okay, but what formal sum maybe is just expression about sum. It's just an expression. Okay. Make sense? Okay. Okay. Later on, you will see that why it makes sense to define this kind of thing. Okay, why does it make sense to define this kind of thing? So another main thing is last time we introduced this. So there's a chain of strictly decreasing ideal here, right? You still remember what MP is? So I tell you more about MP. What's MP? Not about last week also. This one over previous week. What's MP? Yeah, the maximum ideal at the point P. Okay? The maximum ideal at the point P. And then last week, yeah, this is about last week already. So last week we proved that the intersection of these MP, okay, from n equals k equals to 1 to infinity is actually 0. Okay, so no one stay forever inside any power, okay, except 0. And then there's one very important thing that we know about our curve is the C, we only take smooth projective curve, okay, which means a smooth variety of dimension 1. Okay, so where we can interpret about this thing here. So basically the dimension of C is 1. Okay, but also we know that because this is smooth, right, it is equals to the dimension of tangent space at every point. Okay, in particular, you can relate it to MP over MP squared. Okay, so that means this MP over MP squared is generated by 1. element because dimension is 1. Okay, and then so let me write down. So P in MP square is a generator. But if you go through the Nakayama's lemma, this will imply that T also generate MP. T also generate MP. Okay, so this part is the consequence of Nakayama lemma. Okay, this generate. And then, so what's the thing here? So from here, we can define that. So for every G in OCP, okay, which is regular at P. Hopefully you still remember what regular means. You can write it as a fraction. Okay, good, very good. Fraction, such that the denominator evaluated at P is not 0. Okay, that's it. So the multiplicity will define of G at P is given by this mu PG here. Okay, what's mu PG here? Mu PG. So this is the maximum of K such that G live inside MPK. So think of it, this definition makes sense or not? Does it make sense? I said that there's no function that can stay forever inside this chain, right? So it must really stop somewhere. Okay, then we can find the maximum one. Okay. Okay. But what's the consequence here? What's the consequence here? What's the consequence here? If it live in, let's say, so what's the consequence here? So let me put a remark here. This is a very important remark. So if G has, let's say, multiplicity K at P, then we actually can write G equals to H times T to the power of K. Okay, because it lives inside that idea. Okay, the MK, the MPK idea. But I told you what? T will generate MP. So who generate MPK? E to the K. Okay, if you don't believe me, try and write it out. And so meaning I can write it as a power and the K power of the generator of MP. Makes sense? Okay, what's this H? So this H is just some element in the ring. Such that HP is not 0. Okay, if HP is 0, you can pull out the T again, right? Okay, so you can reach to the stage. HP is 0. So think about an example. For example, your MP, right? I think you should always remember one of the MP, right? For example, M of the origin. What's the M of the origin? This one you have to remember. This one is now set as that. M of the origin is 3,000. M at the origin. Maximum ideal of origin. 0. Huh? Generated by what? Don't know what? X1, X2, S3, the coordinate function, right? Okay. Yeah. Very important, this fact here. So meaning here also the same. Then this is the this generator will vanish at P. Okay. So meaning what? What is this? I write G as some H times the factor that vanish at P. So meaning this G takes zeros at P. Okay, at this point T. A complex analysis, did you learn or not? Zeros, order of 0, order of 4. This is the same idea. This multiplicity. Okay, it's the order that you mentioned complex analysis. Again, order of 0. So actually, here we are picking out the order of 0. Can I pick out order of pole? What do you think? Now I got order of 0, right? Can I think of a way to introduce 0 of poles or not? What's the difference between 0 and poles? Huh? How to get poles in your complex analysis? Divide, right? Lorentz series. You divide, right? 1 over x, for example. 1 over x got the pole. You divide by the maximum ideal. Okay? So, if we can say the multiplicity at the pole is negative, okay, of the this thing, then we can extend this definition. Okay? So that our v mu p here really something live inside Z. For the positive part, your negative part. Positive talk about zero, negative talk about poles. Okay, later we will do that in a proper treatment. Okay, so actually not later, now we're gonna do it. So for every rational function, okay, which is non-zero in our case C here, French function field, the multiplicity of f and p is actually defined by v mu p h, which is mu p g minus mu of ph. Okay, where what's the relation between hgp here? Sorry, fgh here. So if we have this fraction form, f equals to g over h. That g and h live inside the local of CP. Okay, so if vp of h is greater than 0, we'll say that f has a 0, okay, of order mu ph. Okay, p, if this order is less than 0, we say that, right, if this multiplicity is less than 0, we say that it has a pole, okay, of order minus mu ph, because we have a minus for it, so to compensate it, we put a minus again. Okay, so it's the complex analysis thing here. Okay, so we actually generalize. So the idea of algebraic geometry, right? At least from the Grothendieck point of view, when we do these schema, Shiva, some more advanced algebraic geometry, is we try to include every field, complex analysis, differential geometry together. We can study them all together. Makes sense? And so we try to put all the idea, okay, into algebraic geometry. Okay, so right, so you can see that, oh, this definition relies on how I put g over h, how I write down this g over h here. What do you think? Does it matter or not, this representation? Okay, let's say at this point, right, I have x minus p to the cube. Okay, and then maybe bottom got s to minus p to the 6. So this function got a 0 or got a pole? Got 0, got pole again. But through this definition, what do you get? 3 minus 6 is minus 3. It says got pole. But in reality, right, what can you do in reality? You can actually simplify it. Okay, so that you really has a function with pole and p. Okay, so what's the general proof of this? Okay, so maybe quickly write it down. Okay, so what's the general proof of this? So the idea lies here. So let's say if f equals to g over h and g prime over h prime, it's really saying that gh prime equals to g prime h. Okay, but from here, how do you deduce? This two function is the same, right? So we can really say that Vp of gh prime is equals to Vp of g prime h. Okay, but is it easy to see? This Vp actually, I can't say that it's multiplicative property, but it's a homomorphism. Okay, it's a homomorphism to Z. Okay, so meaning I can write like this. You try think of it. Does it make sense or not? Why is it the multiplicative become addition here? What are you doing for your VP? Counting the order of 0. So if you have two products together, you have to count how many times, right? So do you just add it up? You just add up. You just add up, right? Okay. You can write down the proof anyway. But from this, right? From this line is already enough, right? What can you see? It just says that G minus GP, this one is H. Sorry, mu PH equals to mu PG prime minus mu PH. Okay, so this is a proof irrespective of representation. Does it make sense? Okay, this is how I just now the example told you. Okay, the very simple example that told you what happened here. So actually, when you do the cancellation, right? So where does the cancellation step appear in my proof just now? What do you reckon? Where the cancellation step appear just now? Which step talk about cancellation here? What do you think? From this specific example here, which step of here talk about this cancellation? What do you think? Which step represent the cancellation I said just now? Huh? I have it. Last step? No, this step. This is the explanation to your high school why you can do simplification like that. 切切. Because you cross multiply is the same thing. This is how we define fraction, right? In university. Okay. So this kind of defining fraction is exactly what you are being told in school that, oh, the same factor can cancel. Does it make sense? Yeah. All right. So from here, actually you can guess a few property of this multiplication map here. Okay, so we can see that the multiplication at P really defines a map from KC. KC cross. Okay, we take the 0 away to Z, such that we send F to BP. Okay. So with this property here, so this is a homomorphism property actually. So first property we already discussed just now was VP of the product of two functions can split to VPF plus VPG, where you just count the order, how many times. And then second, how about VP on the addition of function? What do you think? I guess this here for those who have studied matrix space here. Triangle inequality, huh? Not quite. You can try out whether triangle inequality works or not, but not quite. I think we've got something weaker than triangle inequality, I think. Weaker. Huh? Minimum, huh? Why is it minimum? Can you tell us why is it minimum? Huh? What? Why is it minimum? Why is it minimum? Just now we said that it's counting the order of 0, right? So if this one 3 times, this one 6 times, then together how many times? 6 plus 3, man. Don't you need to factorize, man? Huh? Don't you need to factorize? Let's give some example. Let's say this one square plus s cubed, right? Then you need to tell, oh, this function die at 0. I mean, like, sorry. So it has a 0 at 0. Okay, 0 at 0, how many times? Counted with, let's say, multiplicity. Right? Don't you need to factorize out? So you get 1 plus x. So you got a 0 at 0, and then you got a 0 at minus 1. So how many times? 2. Where do you get the 2? Minimum. Pull the factor out. Make sense? Okay. So general proof also like that only. It's just like that. Okay, general proof is also like that. So this kind of map, you map a product to a sum. Okay, I mean, yeah, map a product to a sum, and then the sum have this minimum inequality here. This map is what we call a, and such map is what we call an discrete valuation. Okay, for discrete valuation on the field K. Okay, discrete valuation. Okay, so the proof, I'll leave it for you to prove. So, from this definition, right, what can you observe actually? So, how about the element in all CP? So these are the things we pick from fraction field, right? Okay, pick from fraction field here. Okay, we pick from fraction field such that actually these VF should be greater or equal to 0. Okay, and then together we put the 0 back. Okay, because our evaluation map doesn't care about 0. And then how about maximum ideal? Maximum ideal. How about maximum ideal here? Can you describe it using this map here? Greater than 1, why? Because all your function in your maximum ideal has 0 at p. So it's strictly greater than 0. Okay, obviously 0 is also still in there. Okay, so in this case, for this reason here, so if you have things that have a positive part, we will call all CP a valuation ring. Got value 1, this ring here, got value. This discrete valuation give it a ring. So give it a value. Okay, there's a value on this element. 多少钱呢？ Okay, positive. Always positive, right? Our Z BVF is always positive. And then why is it discrete? Again, why is it discrete? Because it's an integer. Okay? If real number, then you won't call it discrete. Because it's integer. Okay. So for general nonsense, which we're gonna oh, I remember what I'm gonna say just now. Okay, let's talk about this general nonsense first. Later I'll tell you what happened. Okay, I remember what I want to say already. It's about nonsense. Okay, before we take a break, let's go through quickly. So in general, right? In general, okay, from this kind of construction, we will say that an integral domain is a discrete valuation ring if the fraction R has a valuation, okay, which is a surjective homomorphism. Let's look something like our discrete valuation just now, which actually sends non-zero element to some z, and then we said that it will send 0 to infinity. Okay, and then satisfy the homomorphism property here. Okay, then we will call R a valuation ring of V here. So this discrete valuation. Okay, and then this nonsense here, I don't know whether I want to do it in tutorial or not. If actually, okay, before that, so if A is a Noetherian local integral domain of dimension 1, then all these things are equivalent. Okay, so all these things are equivalent here. So if you are a discrete valuation ring, actually you are integrally close. So what does integrally close mean? So basically, it's a bit like algebraically close, but the polynomial, the minimal polynomial you consider here is always monic. Okay, so integrally close. And then it's a regular local ring. So last time when do we talk about regular local ring? It's about dimension property. So the dimension of this ring should be equal to the dimension of m over m squared. Okay, so that we can call it a regular local ring. Local ring here obviously, of course, refer to this m to be the unique maximum ideal here. But actually, this is local, right? So there's a few word here, Noetherian, local plus integral domain. Yeah. And dimension. And then lastly is m is a principal ideal. Oh, actually, your maximum ideal is a principal ideal. Yeah. I think this one has something to do with the dimension. This proof is really commutative algebra. So last time, remember, I had a lot of concept in the dimension chapter, right? Okay, that uses commutative algebra. Actually, I try and go and pick up the whole story. The story is pretty long. So I don't think I will make it into a tutorial, but I think for the sake of completeness, I want to make a commutative algebra sheets. Okay, so that there's enough commutative algebra that no need to learn for the sake of this course, but for the sake of understanding, you should at least go through it so that next time in future, when you go and do more serious maths, right, then you look back, oh, actually this is the flow. Okay, but for the sake of this course, not. Okay, I already see a lot of algebraic geometry course set up at least for this kind of introductory course. They cannot avoid using commutative algebra result, but they will keep it to minimum. Okay, this is what we will do also. Okay, so to do really proper algebraic geometry, you really need to have some commutative algebra. Okay, otherwise, you can just do the geometry axiom and then just play with line and plane. That's it. Okay, so yeah. Okay. Yeah. So what? So how about we stop here first? Okay, any question? No. Okay. Yeah. Okay. Hey, come here. Okay, let's take a break. Let's break until 106. Hey, come here. Oh, 刚刚星期五打毛球，我说这个公司可以订场，我不知道啊，你不知道？没有，我们在订场里面还没有场啊，因为我们去年去打就是没有场啊。我外面打没有，我应该没有让海明打，就叫他们就学生啊来打。可以订得到场啊？超场不是订得到那个羽球？可以订，你有什么理由订？可以没有，但的话不是全部人都可以订，但是就是要有，就是要需要有人帮着，不是因为其他学生可以完全如果但是是什么名义？如果打球的话，就不是全部人都要订，没有其他人又找不到老师来帮他们订啊。对，就是会对。还有我们这样现在的店可能要办个体育相关的。可以下个礼拜办。但是下个礼拜办，这个礼拜办我最后一天。对，这个就跟着羽毛球。对呀，对，我们那本来要钱。人就要现在5块。能够订吗？看看星期五，最后一天要反正。对啊，就看这两个人都有。其实如果订不到，我们也是要打的。对，跟怎样就是有在就打了。不是，但我觉得会有人就比如说就是来其他学生就来工资对的，是那个球场。没有，如果我们早一点打的话，就是虽然我们订了，但是其他人不知道。对。跟其他比赛，我们如果有人打，我们就上去点标多分。但是我们现在不行的点是谁分的？但是如果我那个因为可能还是这个。 没有，上次我们开始早点上，对，我早就没有，没有到早上2点8应该上够的。上次就是2点开，那时候应该是3点多。反正我上周六到上周六到，你是一个人来过。周六我是周二有些的问题的，但是有些500比他还好。我刚已经有说了，我不会回去，然后其他人也会这样的话就是都人，对，其实就是要不都人都人。因为正常一样，有的时候如果我们早点来，也得来到8点。上次是我有课，对，他讲有词。什么？
下午可能有事情，下午可能有事情要执行。
你有事情啊？
下午。
你是什么？你不方便？你是哪一组啊？你是哪一组啊？
第一组。
你是第一组哦，你是讲你 present 过后你不能留到下午。
对，就可以在星期五来考。
OK，
星期五那我星期五下午可以。
哇，对，其中我尽量是。
对啊，这样你回去做吗？
我家人。
你家人啊？
家人。
哦，要用到车的。所以车现在是给你开过来这边。
对。
OK 啊，我觉得 OK 吧，可以吧。你是 clan 是吧？clan，你可以跟他一起来哦。你可以跟他一起来。
来不及啊！
什么叫不来不及？
你打得太快啊！
没有，他每天来回啊。Adrian，他拜六如果没有车来，你可以载他。他拜六。他也住在 clan。叫他去你家，还是怎样？在啊，我在啊，我等下在。他下午没有车来。啊？8点呢？肯定他也要找啊。
我前2天是5点了。
你几点出门？你跟他讲啊。
我6点让他走啊。6点就要走。起来一点。人要载你哈，那个。
带他去你家还是怎样啊？你是可以。
我抓去我家。
不知道你家远哦，
别路啊。太多红绿灯。
还是去一个地方也是可以的吗？要经过那个地方。
他也有车啊，他在你。
他没有，他如果把车开回家里，然后他家人就有车。他只是下午的时候他家人要用车，所以他被逼。如果来，他可以跟你来，他就车直接交给他家人了。跟你回啊，不然。哦，
跟我回。
跟他回啊，反正你留在这里。你周末就没有在这边，可以跟他回，跟你回啊。你不是要回巴塞吗？几块？很奇怪。碰车 I mean like 碰车。他每天来回。对，不然他已经来回了2年。啊，不止3年了。foundation
就是的。
真的，在那个超冰，
那个吃有点
哪一个啊？
超冰有吃的，还是很好哎。
那好吃是一个类啊，因为它的那个玛莎跟那个
是一拿那个100元。
也可以是巧克力，但是巧克力里面有 brown， 玛莎里面就会是 Algebraic。我以为那个冰淇淋是玛莎口味， 丢不是，
加厚
不是，它是只是放粉，然后淋那个东西嘛，它里面是奶来的，那个奶的，
哦
它不像那个铁观音哦，好像铁观音是，然后乌龙也是，
就是啊，我操，
它因为它讲的里面那个冰是
它并不是抹茶来的，
它淋的那个也是很浓了。
啊，那个算浓啊，我觉得比较特别的是那个 chocolate，因为它里面是 brown 对吧？
我觉得算挺好吃的。
天哪，
真的，
可能还有更好吃的，我带你去吃。
那个沙比吃好吃的，我会觉得吃，就是不，我都跟你讲，乌龙食物是补补吧。
没有，我们是他们讲好特别吗？
这样子特别 overpriced。
哎，也是算我
地沟船，
那有点贵的，就贵难吃一条啊。
哎，价买全部甜品啊！
没有，可以啊，呀，你吃已经要100，对哦，
那 I told you guys don't come to me。
是他们讲还有一节150的那个会，
我们都承认。
不是那个青色招牌的那个烧蟹什么村还是屠龙烧蟹，
乌龙自己也不吃。
去吃那个华人餐啊，
这也是吃那个中国餐好吃吗？
也是中国
可以写，
确
可以写，
它不便宜啦，
也不便宜
挺贵，
美的好吃
就是 OK 哦。
至少好吃。
，OK。
那个
就是中国菜，在那个地辣爆点比较更多菜。
我觉得它比辣爆点好吃点，可能它的包菜没有像辣爆点一样好吃，其他应该比辣爆点。
其实我们最近去吃那个包菜没有很特别，我感觉。哦，
这种
因为真的没有感觉。
可能
那是在
我跟你讲，廉价干锅啊，不能吃的。
没有吃过哎，
加上我麻辣烫还干锅不能吃。
是那个公寓也在远远的，在那时候有个吃去那边的时候，我在
哦，是吗？你在那个十字路口那边啊？
对，是不是路口地北危险？
没有，我那个路口根本出不去，那左右那。
因为左右然后有人要转一个，
没有问题是那个转上来的没有红绿灯挡住，然后就是电梯。
全部没有，
感觉
因为那个十字路口是完全没有。
有啊，我的那个有啊，我的那个
是的嘛，那边咖啡是蛮难的，
是吗？
本来
没有弄，
本来那边是不多车，只是
我现在很多人。
人去那边。因为我这边见过龙狗，要去那边我见过龙狗，
不是你见过我去走路的还是？
想说
那条山，你知道那种龙沟是那铁吗？
哦，
因为那个concrete的那个洞那边，
啊，
我整个脚跌进那个
为什么？
洞，
不能裂掉，我猜到。
然后那个厨师还笑我里面有鱼会咬掉我脚。
嗯，Okay, so let's continue. Yeah. 现在开始讲。Okay. Okay. So next we'll go pretty fast because I don't want to waste too much time here. So the first lemma we will see here is if you run the non-zero function, okay, actually the zero you get should be just finitely many. Okay, finitely point P in C such that VP F is not zero. Or not just zero, but also the poles. Do you have similar result in complex? A function has only finitely many poles. Do you have that? Finitely pole or finitely zeros? Huh? Do you have that result in complex? What's the segment you had then? Meromorphic? Something of meromorphic stuff? Or holomorphic stuff? Okay, so the why we have finally many points here is we just consider curve here C. Okay, and then the zero and the poles are actually proper closed subset of C. Okay, but C is curve, then you only have really finally many points here. Okay, a bit like fundamental theorem of algebra. Okay, so you really only have like many poles of zeros. Okay, how to see poles? Actually, it's just 1 over the 0. Yeah. Okay, so it's another 0, but 0 in the denominator. Okay, so from here, what we define is the divisor. Okay, so we'll define what's called the divisor now. So the divisor defined by F, okay, is really given by, we will write this notation, bracket F is not a ideal or what, bracket F here, okay, divisor defined by F, defined to be all the point in C such that VP F times P, okay, is lived in div C here. Okay, so the ni coefficient here is the order, okay, order of 0 or poles. Okay, so the point here we consider is whether VPF is not 0. Okay, so these are the 0 and poles. So many divisor defined by function is basically you list out all the 0 and poles and then put the multiplicity on this. Okay, so just now the lemma is pretty important. No? If there are infinitely many poles of 0, what happens then? Then you will deal with an infinite sum. And so here actually is a finite sum. Okay, bear in mind now, the setting we set now is everything is about curve. Okay, it's just dimension 1. Okay, so you see here, you dimension 1, you list out the point. What's the dimension of point? 0. Okay, so this is a core dimension 1 thing inside your curve. Core dimension 1. So 1 minus 1 is 0. So this is the dimension 0. So in general, you can define divisor for general variety based on this, the difference about dimension. So if you always have if you list out as a core dimension 1 variety here, then this is called divisor group. Okay, in general, because in higher dimension, right, you not only look at core dimension 1, you can look at core dimension 2, 3, 4, 5, 6. Then these define a different group. A different group. Group here, I mean the actual algebra group. They really form a group. Okay, this divisor. Okay. Later you'll see that these divisor, right, will form something called the divisor group. Okay, or sometimes they call it divisor group. Okay. And then if you look at different core dimension variety, right? Yeah, then they will call it a child group. Okay. Yeah. Next, we say that the divisor D in div C, okay, is called a principal divisor. So divisor in div C basically is just some formal sum, right? We don't know where it comes from. If we know that it comes from some rational function, okay, such that f non-zero, then live in fraction field, such that d equals to this divisor of f, then we'll say that this d is a principal divisor. Okay, if I can realize it from some rational function, then we will call this a principal divisor. Okay, in general, divisor is just formal sum. That's it. But if it comes from some f, meaning there's a meaning to the coefficient, they are actually 0 or something. There's a multiplicity of 0. There's a multiplicity of poles. Then we call it principal. Make sense? Okay. So maybe how about we play some game. So the game here is, can you write down the example of this? So let's say we have this coordinate in P1 here. Okay, and then we look at a map in the fraction field. Okay, x over y here. Can you figure out what is diff w here? Can you look at this? What's the diff w here? W here. So you need to figure out what are the zeros and what are the poles. Okay. But how does the point here looks like? This is P1, right? It's a line actually. Okay. So what are the zero? What are the poles here? You need to figure out zero and pole first. Only then you can figure out what's the multiplicity. Okay. How do you make x zero? How to make x zero? X has to be zero. Okay. If x zero, y can be zero or not? Cannot, right? Because this is a projective space. So your zero is 0, 1. Okay. Your pole 1, 0. But what's the coefficient here? 1 and minus 1. Okay, so this is a divisor of this function. Okay, so can we play a different game? Let me see. Let's play a different game, okay? Wait, I can't find my example now. I thought I can work backward. Wait, should I think of one? Working backward maybe got a lot of possibilities. But let me see. You know what I meant by working backward? So I give you a divisor, go and find a function that can realize this, meaning show that it is a principal divisor. But I think that one got a lot of possibilities. Okay, but anyway, you get the idea now? Okay, I don't want to give you more example. I will put it in the lecture note. Okay, so proposition. There exists a group homomorphism from KC star to diff C, okay, where we send F to the divisor. Okay, this is the group homomorphism. And then this DC here, well, this so then these principal divisor will actually form a subgroup of diff C. Okay, so what's the group operation diff C? Just now we say former sum. Okay, so it's an addition. So what's the inverse? Just minus of a function. Okay, so this is a group homomorphism, right? So who is the inverse on the rational function field side? So just now we proved that, and have we proved it? So divisor of fg is what? So the claim here is this is equals to the divisor of f plus divisor of g. Because just now the multiplicity property, right? Vp of fq is equal to Vp of f plus Vp of q. That one split your multiplicity into sum. So that's why we can split out the coefficient here. And then how about negative f? Who gave you negative f? What do you think? So you need to think back. Where do you think? Think about the coefficient. How your coefficient can swap, become positive, become negative, negative become positive. What happened? This corresponds to what kind of swap? The positive, negative refer to what? Poles and zero, right? So if you swap positive, negative, zero and pole, swap. So how you swap zero poles here? Inverse. Okay, you just take 1 over f. Correct, no? 0 become denominator, and then the 0 in the denominator become the 0 in the numerator. So the point 0 sum. So try write down this proof here. Okay, so this is the idea. Okay. Next, so we'll say that two divisors are linearly equivalent. Linearly equivalent if their difference is a principal divisor. Okay, so we'll say that two divisors are equivalent or linearly equivalent if there exists a f in kc star such that d minus d prime equals to divisor of f. Just now we said that so just now, okay, so wait, before that, so let's write down this as a equivalence relation. So it's related. So you can prove that actually this is an equivalence relation. Okay. So in other words, how do you reinterpret the principal divisor in this relation form? How do you interpret? So if you are equivalence to, if you are a principal ideal, what thing you're equivalence to? What's the thing you're equivalence to? So if you are a principal ideal, that means that D equals to divisor of some F. Okay. So if you are D equals to some F, you are equivalent to who? You take what difference? D minus what equals to F? Please don't think of it too complicated. So just think a primary school way. So I just now said a principal D equals to F, right? So minus what equal F? 0. 0. Okay, so we have D is equals to 0. 0 divisor, if only if D is a principal divisor. But what's the 0 in the divisor word means? What does it mean? All the coefficients are 0. Okay, all the coefficients, yeah, there's a 0 function there, right? Okay, all the coefficients are 0, so it's really a 0. Okay. Then prove that actually this equivalence is a equivalence relation. So in maths, I think there's no accidents. Whenever we talk about equivalence, it's always an equivalence relation. So you should show that why the three things works: reflexivity, transitivity, symmetry. Okay. Okay. So to this end, so once you have equivalence relation, what to do? It's the same story one. What's the point of equivalence relation? We want to group things together. Okay, so we have a equivalent class. So we will define the divisor class group. Or I think somewhere it is called a pickup group. Okay, of C is defined by C equals to if C, okay, quotient out by this equivalence relation. Okay, or somewhere they write it is a pickup C. And actually, this is an invariant of a variety. For now, we just define it for curve. So just now I told you, right, different paces, divisor could be different core dimension variety. Can you imagine if I put a different dimension variety here? Can you imagine? This is just a point, right? Point is like maybe x minus p, the zero set of this thing. But the variety you learn is like there could be something a surface, right? So it's like hyper surface like that. So if I increase the dimension of my C here, it's not curve anymore, higher dimensional variety. Then here the dimension, the sub-variety that I consider here could be different, no? More than a point, no? Okay. For example, if I consider C to be a surface like that, I don't want just to talk about points, maybe I want to talk about lines inside here. Okay, so instead of point, I can talk about lines, formal sum of lines. Okay, line as what? As a VF, okay, VF of your F here. Okay, maybe not the same F, here is a different F1, maybe. It's one of the factors. Okay, then this will define a different group, what they call a child group, okay, with a higher dimensional sub-variety here. Makes sense? Is it the idea going well or not? Okay, so for now, we just care about points at the moment. Yeah, it's just a co-dimension 1, and then we live in a point, the world of points. Again, our variety is just a line curve. Okay, so point on the line. Very simple one, the most simple case. Okay. Right. Right. So in this case here, it's not hard to see that this group is actually a abelian group. Okay, why is it abelian? Because the group that you started with is already abelian. Formal sum is abelian. But you quotient out by this abelian group some more again. Okay, it's still abelian. Okay, essentially it's an abelian group. Okay, very nice group. Okay, abelian group is very nice. Okay. All right. So what should we see next? Okay, I think we should see this result. Pretty important. So this is the first non-trivial result we see. So let's see the projective one space. Okay. Then what we claim is in div C, we have that D is a principal divisor if and only if the degree of D is 0. Okay. What's the degree of D here? This is the degree of a divisor, right? So last time, how do we define degree of a divisor? So there are few degree here in this course. There are degree of function. Okay, then this is the degree of divisor. So what's the definition of the degree of divisor? Basically, you just add up your coefficient. That's it. So meaning what here? If you add up the coefficient, meaning the multiplicity coming from the 0 and coming from the poles, they will cancel out. Okay. This is counted by multiplicity. I didn't say the number of 0 and number of the number, I mean how many of them are. The number of distinct 0 or number of distinct pole. This is added with multiplicity. Makes sense? Maybe x minus 2 has a power 2. So we will count this 0 twice instead of 1, 2. Okay, with multiplicity. Always now we will count with multiplicity. So to see this, what do we do? So to see this, not that. I think this is something we proven, if I'm not sure, I'm not wrong. So every rational function on P1K here actually can be written as f equals to g over h. Okay, for some homogeneous polynomial. GH in, let's say kx0, x1. Okay, if you remember, we talked about the graded homogeneous ring last time. Okay, and what's the key point here? The degree of G and degree of H must be the same. Okay, if you still remember last time. Okay, so in this case here, degree of F actually is 0. The degree here is the degree of function. It's not the divisor. So this degree of F is defined to be degree of G minus degree of H. The degree of G and degree of H is just the degree of your polynomial. And because it's homogeneous, so we know what's degrees. Okay. Okay. Wait, let me see. Yeah. So this degree of f, how do you imply that the degree of the divisor is 0 here? The principal divisor here. How to imply that? How to imply? Is it easy to see? The top power and the bottom power is the same. So if you want to use fundamental theorem of algebra to split up, very hard to think. Very hard to think. So what could it be? If a top degree is the same bottom, same with the bottom degree. Like, so sorry? Yeah, what kind of degree is 0? So my question here is how you convert the degree of a f to be 0 to a degree of a divisor to be 0. This is my problem. There's 2 degrees here. Top degree and bottom degree is the same. And then you go and find your 0. Right, let's say it's the FTA, you can find all the 0. Then how many 0 you should find? Top and bottom should find the same number of 0. Okay, so they cancel out. Okay, when you make it into poles and zeros. Okay. So next, how about the other way around? Let's say we know that they have the same number of 0 and same number of poles. What could happen? So what's the form that this D could take? Okay, the form of D could take is we can group all the 0 together. We can group all the poles together, right? Okay, so we can write it as the sum of NP for some NP greater than 0. And obviously, we can also write it as D prime prime of NP, sum of NP times P, where we take NP to be greater than 0 also. Okay, we group the pole together with the 0 together. Then, how could they cancel out? How could they cancel out? Sum of NP should be equal to the sum of NP. Okay. Yeah. Okay. Sorry, a bit of abuse of notation here. I use the same P, but you should know that they are different. This is just indexing. Okay, just indexing. Index set. Although index set should also be different. Okay. So what does this mean here? So actually, the claim here is there exists homogeneous polynomial G and H of degree abuse of notation, or not abuse, okay, because they are the same, I call it N, which actually vanishes precisely on D prime and D prime prime. Okay, here is an abuse of language. He'll tell you what's this mean here. So because D is defined by some points, right? So vanish on the divisor, meaning vanish on those points. Okay. So what's the F we could say? So we just set our F to be G over H, such that we will get this divisor defined by F is equal to D prime minus D prime. So actually, this is a very special property on our P1, such that you can always find a polynomial to realize these zeros. Okay, a bit like FTA actually. Yeah. but the result of this is very important. So this actually tells us that the degree function actually induces an isomorphism. Okay, so this is an isomorphism between the divisor class group of P1 with Z. Okay, so this is another way you see Z. No? Okay. This is a different group to see Z. Okay, makes sense? So yeah. Okay. Basically, this is the only thing we can do here, because our divisor group definition is very restrictive on a projective space. If you want to go to different spaces, we should have different definition of divisor. Only we can do stuff. For example, there's a fact that a divisor group of AN is 0, is trivial. And then the divisor group of a product of PN is product of them. And divisor of PN, this one is P1, right? Is also Z. So actually behave the same as P1. It's the same argument here. It's the same argument, but you increase that much. Okay. Well, like your subgroup must be what? Must be a quotient of Z, right? Because just now is it? Yeah, because the degree actually map. Let me check. So degree is a map from a divisor group to Z, right? To Z, yeah. So you are always getting a portion of Z. A portion of Z. Not quite how, because I told you that the divisor class group of product P and is product Z. Okay, let me see. Oh, actually, I think it depends on the degree you define on the divisor as well. Yeah. Okay, it depends on the degree you define on the divisor. Okay. The next part is okay. To get to Bezout theorem, there's one very important result is actually every principal divisor has degree 0. Okay, just now we said that there's a if and only if result in the P1 case, right? But one direction is always true. Okay, so every principal divisor has degree 0. Okay, so to prove this, there's some concept going on, which I don't want to spend time, but we will quickly go through it what we need here. Okay, see. Okay, so we need to first define this surjection map, degree of surjection map of a map. So this is a new kind of degree of such F. This is an F between projective curves. Actually, you count the degree of extension, okay, between these two function field here. Okay, so the claim is this extension is always finite. Okay, so this number is finite. Okay, and then these two have a transcendentance degree 1. Okay, so their field extension is finite. And then next lemma to establish is every non-constant function from C to P1 is surjective. This is actually a very strong result. But the proof, let me see the proof. The proof is using the result that I told you last time, where we got proof that O of projective space is K. You still remember on the O of projective space is K. So the constant, only constant function live inside your local or your regular function. The global regular function. I think this also reflects your result in complex analysis. Your holomorphic function on a bounded set is constant. Is it? What's the statement? Eric, what's the result in complex saying that function is always constant? Entire bounded, okay. Do you have restriction on your domain or not? No. You forget. Huh? NIT on? Whole C. Okay. Yeah. Yeah, entire. Okay, good. Okay, and then next. So this term here, local parameter, if I got chance, I will introduce in the tutorial. So basically, they call the generators inside the maxima ideal as a parameter or local parameter. This makes sense, right? Because if you look at the maxima ideal of 0, right? These are the x1, x2, these are the coordinate you use in your R2, R3, Rn, right? In particular. Okay, so they call these generator as a local parameter. So basically, what happened here was, let's say you have a surjective map here, okay, and then you pick a local parameter t in q, so meaning there's a generator of your mq. So basically, it's a function defined on q, okay. Then the inverse image of this f inverse, right? So f is a surjective map from C to C prime prime here. Why I got 2 prime, just 1 prime. Okay. So inverse image of this is another closed subset. So it contains only finitely many points here. Because C is closed. Inverse is closed. Do I require more? So we set this f star q is, so f star q, where's the q come from? So q is a point in C prime, okay? But f is a map from C to C prime. But you want f to map on C prime. So you want f to act on the core domain. How is it possible? Okay, so actually this is a pull back. So how do you pull back here? Well, how do you pull back? Very important. So you want to pull back to C. Okay. So this f star q, right, is a divisor. Okay, it's a divisor. Okay, defined as a point, sum of points inside the pre-image of q. Okay, under f. Okay, this makes sense, no? Right. So f, how to add a core domain? Oh, this is subjective. So every point in a core domain, I can find out the inverse. Okay, so this is the PI here. But how to put the coefficient? Okay, how to decide the coefficient? Okay, so to decide the coefficient here, we look at this function here. F star t. So again, another star. 2 star here we got. So 1 star add on q, the other star add on the function t. Makes sense. Can f add on the function on where q is in C prime, right? Okay, C prime. Cannot. So T is a map from C prime to a field. And then F is a map from C to C prime. So C to C prime to Q. So together you get a map from C to Q. Then you can ask about the zero of this function. So you're asking about whether the pre-image of this Q is a zero or a pole of this function or not. If it is, write down the multiplicity. And then you form this divisor. Make sense? Okay, so it's a very specific function you look at this MQ here. Okay, can you understand what I say? Okay, the MQ there, obviously Q is the 0 there, correct or not? Because it's a maximum ideal defining that point. Q must vanish at that point. So now you are looking at pre-image. If I pre-compose with F, is this inverse image still a 0 or a pole for my pullback of T or not? It could be, it might not be. Okay, makes sense. Okay, understand what I say? Understand? So this T, again, this T is a generator of MQ, right? So definitely this T must vanish at Q. Could be some X minus Q, something like that. I think have to be this one. I mean, you can choose a different one, maybe 2 times S minus Q. But, okay, so then I pull back off. Okay, I apply F first and then apply this thing. Apply F first, apply this thing means what? Basically, I just evaluate at X minus Q. Correct? Is it what it means? Not quite. Is it? Oh, not quite. So you do F first, okay? You send C, maybe X, Y, Z, go to something else. Okay, and then you evaluate your T. Correct, huh? Correct, right? Wait, so let me write down. So this is just T evaluate. Yeah, I write it here. Okay. And then you ask, oh, is this PI 0 or a pole? Okay, then get the multiplicity out. Make sense? Okay, so this is the function you consider instead of T itself. Okay. Layer. Some of NA. Okay. Right. Yeah. So the problem is, you see, we pick representation here again. Okay, doesn't matter or not if I pick different representative. Okay, if I look at different representative, let's say T prime. Okay, but T prime and the ideal generated by T and T prime is the same. Okay, but doesn't matter or not. So you can prove that, or actually it doesn't matter because it differ by a unit, but unit won't vanish at any meaningful point. It won't vanish, basically. So the VP there is 0. Okay, so it won't contribute to your multiplicity. Okay, so the two representation will differ by a function which is a unit. Okay, but unit last time I told you already, right? If let's say unit is 2, who can vanish at 2? Nothing vanish, because it always have value 2, it's not 0. Cannot go to 0. Okay, so the contribution from that part is 0. Okay. Okay, so from here we can extend linearly. We obtain a group homomorphism from div C prime to div C. Because just now we define it on a point Q, right? So you define on different Q, okay, and then extend it. Okay, extend it into a homomorphism. Because div C prime is just a bunch of Q together plus multiply with some multiplicity. Then you extend linearly means what? You keep your constant, you keep your sum, you just evaluate your point. Okay, F apply on those points. Then you get another bunch of points with multiplicity again. Make sense? Does it make sense? 懂我在讲什么吗？ Something like this. So N1 of Q, right? Sum of NQ of Q. Okay, after you evaluate, basically you just apply F star to your Q. Yeah. Right, this is what it means. And then keep your constant, keep your extend linearly. Make sense? So this is equal to F star of sum of NQ. Okay. Brutally define a group homomorphism. Okay. Okay. Next is a very important result here. Okay, we're not gonna prove as well. It's a long proof, I think. Very long, actually, it's a super long proof, very technical proof. But the result you must remember here was, if you have a surjective map, actually, for every point of Q in C prime, the degree of F star Q here, so the degree of F star Q here makes sense, because it's a divisor, okay, the degree of divisor, will be equal to degree of F. But this degree of F is just what we define, is the degree of extension. So the degree of extension is actually the degree of F star Q. Okay. It's kind of counting the inverse image. Kind of counting the inverse image. Okay. But this is true for all Q as well. Okay, this is true for all Q as well. So meaning you calculate one of them, you can get the rest already. Okay. This is like, let me see, did I put a remark here? Oh yeah. Okay, so you need to go through some technicality that we don't want to go through. Because you see, there's a module stuff inside here. Yeah, I don't want to go through. We don't want to go through it. Okay, so the above result actually give a geometrical meaning to the degree of a map, the surjective map. It says that the degree of F is the number of pre-image of any point Q. Okay. So once you know the number of pre-image there, corrected. So correctly corrected here means count with multiplicity, because just now for the mu p, right? That's why it's count with multiplicity. Okay, this is an instance of a link between algebra and geometry. Okay, one is the degree of extension of the field extension. The other part is just counting how many things inside the pre-image. Okay, makes sense. So pre-image here obviously need to as a zeros and opposed, okay, and then with multiplicity. So far, okay or not? How many times we have? Actually, no more time. But I want to finish up. Okay, I want to finish up the result here. So then what we can prove is if you have two smooth curves, okay, and then if C prime is projective, then every rational map is actually a morphism. Okay, pretty interesting result here. Okay, every rational map actually is a morphism, which you can write it as a polynomial form. Yeah, very important. And then next, then the corollary is two smooth projective curves are isomorphic if only if they are bidirectionally equivalent. So actually, in the projective curve case, isomorphism and bidirectional equivalence are equivalent. Okay. And then only then you can pull the result to prove this. Okay, this proof actually become very easy after we set out this whole thing here. Okay, maybe let's run through this proof. This is the last thing we do, and then tomorrow we will go to Bezos. Okay, so how to prove this then? So if C is a smooth projective curve, then every principal divisor on C has a degree 0. Basically, you need to compute like given you a principal divisor show that is degree 0. So just take one principal divisor, so it's defined by some non-zero function here. But then this non-zero function will define a map from C to P1K. Okay, we'll define a map from C to P1K. So from what we have done just now, actually F is surjective plus it is a morphism. So it's a surjective morphism. So just now we proved that if you have a surjective morphism, what happens? The degree of this F is equals to the degree of the F star, okay, of Q. The Q are on the point of P1K, okay. But what happens here was by the definition of F here, right? We can write this divisor here as a pre-image of, pullback of 0 and pullback of infinity, because we are counting how many 0 and counting how many poles. Okay, so it's actually a pullback of 0 and infinity. But just now we know that a degree of 1 point, the pullback of 1 point is actually equals to the pullback at different points, okay, which is equals to the degree of f. Okay, these three things are the same because your pullback at any point is the same. Okay, so degree of f. But then what does it mean here? So what's the degree of f then? Okay. Well, the degree of f is just all these multiplicity put together, right? Okay, but these are the degree of these f0 and f star infinity. So you take that difference because one is as a pole, one is as a zero. Okay, so you need to adjust your multiplicity to negative. So they are the same, so their difference is zero. Okay, make sense? Okay, so well, how does this result demonstrate in your complex analysis? Have you gone through this argument principle before? Have you evaluated this contour map, df over f? Did you learn this argument principle? Do you evaluate this kind of map? Contour around df over f. What's this doing? This is counting the difference between number of zero and number of poles. Okay, so in our case here, prove that it's zero, but in your case also zero. Okay. Any question? But if you notice, in the Moodle, I also put out the complex analog of this result on the meromorphic function. Okay, so you can see that they also found that the number of zero and number of pole is the same for meromorphic function. Okay, so that's why there's some relation between algebraic geometry and complex analysis, complex geometry and vector. Any questions so far? Okay, tomorrow we're going to use this result to prove the Bezout theorem. What's the Bezout theorem? Hi, Eric, you presented, right? Not you. Who present? You guys present. What's the Bezout theorem? I give you two curves. The number of intersection is equal to the product of the degree of. We're going to show equal in our case. In our case, could be, yeah. In our case, it's equal. Okay, we'll see you tomorrow.